Alright, you are now able to hear me. Let's go. Alright, so we're going to try to do something different this time. We're going to try to stream simultaneously on TikTok and see if that gets us more viewers. You never know. Alright, so checking. We are live on YouTube. Audio's working. Let's start up the background music. Alright, OBS, how's that looking? Sound-wise, let's turn that down a little. Alright. And then we're going to go over here to live. There should be... I haven't figured out how to set up text on this yet. Go with learn. And we're going to wait. No, I want the other camera. Okay, maybe it'll let me switch afterwards. Nope. Un momento, I'll get this working eventually. There we go. Alright, I'm gonna put this on my jank camera stand. And... Alright, hopefully... Okay, hopefully that doesn't fall off. Alright. So, we will see how this goes. Project partially updated. 10 files into commits. Just make sure I can see YouTube chat. There we go. Hello, everybody. Let's get started. So, what we're working on here is we're going to be working on improving the abstract syntax tree and making it so we can actually collapse. How do I describe it? Constant expressions, I think, is the correct term for it. So basically, like, let's say in your code you have something like this. You have like 2 minus 4 in your code, and that is a constant expression. So one thing we can do here is at compile time collapse those together. So that's one of the reasons that we want a abstract syntax tree. Thinking about it the way that whatever. We'll just get started. So for now, I'm going to continue. So right now, if we go over to the compiler, so in the compiler, this is what actually generates the bytecode that is then generated to assembly later. So the way this works is we have all of these visit statements, and this has to do with our parser lexer antler. So it's defined by this syntax file, so each one of those visit functions matches up with one of these labels here. So visit float or visit const float function would match up when we find a float in our code. So same thing for ID, multiplication or division, addition or subtraction, all of that sort of stuff. So going back to here, that's what all of these functions are. They're just one-to-one with what's in the syntax file. And then the syntax file is what actually defines what's going on there. So what we want to do is right now, if we look at a moldiv, for example, multiplication division, what happens is we're just directly generating bytecode in here. So we're appending the code multiplication or division to the bytecode, and then our indexes of the values that we want to operate on. So when we're done actually generating the bytecode, and this is just to give an idea of what this line of code is doing, we get like move instructions, subtract instructions with indexes to the actual variables that are being operated upon. That's kind of what's going on there. So essentially, after we're done, the code will do the exact same thing. However, it will then be easier to optimize and whatnot. So to get started, we need to continue working on our now the term is usually abstract syntax tree. I'm calling this an abstract operation tree because well, it's more accurate to what it's doing. So we just have nodes, like a single argument node or a dual argument node. There are better names for this, for like the specific operators, but I was on a plane as I was coding this, so I don't have that. So we're gonna just keep working on fleshing these out. Alright. So for the addition node, now what was that one function I needed to, okay, so that's the generate bytecode. Optimization, or generate bytecode. And this is a arg node, and we'll pass through arg A and arg B into there. Oh, I still have these as shared pointers. Yeah, we just want these to be regular pointers. Now. Copy that, back to definition. Copy this over, there we go. No longer need to move it because they're just regular pointers. There we go. And now back to micro generation. No, I don't want to. Oh, I actually do want that to be an override. And then this is where we copy over the code from the compiler into the node instead. I have like the super jank tripod setup over there, so I'm just hoping that doesn't fall down. So now, how are we going to represent these values? I think we're going to need to return something from generate bytecode, and this is probably where we are going to want to implement the value index struct that I've been working on, which I have not decided how I'm going to do completely yet. But for now, we'll just add it in. So instead of the value struct, which we are using in compiler, my phone's about to fall off the wall. I'm just using regular Scotch tape, which is, there we go. So essentially, I'm just trying to replace this. You know, why not just replace it? Oh, if my phone falls off the wall, my phone falls off the wall. And we end the TikTok stream. And just continue with the YouTube one, I guess. What was I gonna do? Right. Generate bytecode. We're going to have this return a value index instead. Yeah. Oh, there goes my phone. All right. All right. We're just gonna end this and go to YouTube only then. Alright, where was I? Right, value index, generate bytecode. So this is the, all this represents is the index of the value that was returned by this expression, if there was a value returned. Now I'm thinking about, because I kind of wanted to store value indexes directly in the bytecode instead of just using the unsigned 32-bit ints that I'm using right now. That way I can store extra stuff like the type that the variable is, so I don't have to generate a different opcode for every single different variable. But let's create two different classes, well, two different structs. So we're just gonna have the gonna have a struct AOT value. And this AOT value is going to be the same, essentially, as this value. Because I do want to keep basically all of this functionality, but not just in the compiler class. We're trying to take more stuff out of there. Going to need to actually, let's just class type def. We'll just pull one of those instead of importing it. All right, so we now have AOT value, and then value indexes, we'll still use that only in the bytecode. Then value type and register index. Yes, that's all we need for now. And I'm actually going to set the alignment of this struct. So I'm just going to remind myself how to do that. So it's align us, right? I have to look up the definition of this. Struct align as. We're gonna align this as 2. Yeah, align as 2. Now we just know that no matter which system this compiles on, the struct will always be in the same, it will always be structured the same. So now generate bytecode, AOT, value. And now, here, what we'll do is what did I name them? ArgA and ArgB. Okay. ArgA. Oh, do I not have them set as projected? I do not. There we go. Now we can actually access them. So ArgA, and then generate bytecode script. And also ArgB. Here we go. And then I'm gonna make cast temp we're gonna pull that over from the compiler into here. Cast temp. Just gonna const reference. There we we go. And then we're just going to copy this from compiler. And this just makes sure the operand that the result is getting stored in is actually a temporary value instead of a variable that we actually need to remember the value of, because the way the assembly instructions work is that if you do an addition, the result is stored in the left operand, division, addition, that's how it all works. So you need to make sure that the left operand isn't something you care about. So we are just going to copy this function. Ooh, and we might need to also pass in the script as an argument as well. Yeah. So here we just go. We also need to copy that over from compiler as well. Or maybe... I think that's what I'm gonna do instead. So, instead of... Yeah. So instead of just passing the raw script to it, we're going to instead we're going to pass a compiler context to them. Then we'll have nodes only operating on a single function instead of the entire script. Well, that's how I'm gonna have to do it anyway. Yep. And then this compiler context will contain all the stuff that we would usually hold in this function and then just recursively yeah. So we need to store a script function, which is the current function being compiled. Alright, and then I think visit program is the... No? Might just be compile. Visit program. It is visit function. Okay, it is visit function. Oh, I'm thinking of the... I'm thinking of the linker right now. Not the... I'm thinking of the wrong part of my program. Alright. So we're just gonna take a bunch of the state out of the compiler and shove it into the compiler context. So we have the current script, the current function, and let's not have the types, we do want the scopes to be in there. And I also want to do a thing with value index. I also want to be able to reuse values that we've stopped using, like temporary values. I don't currently have a way to do that. Value. These are like local variables. And for now, we'll just throw value index into here as well. We'll just make this a struct for now because basically everything is public. So we have value index, current function, the definition of a scope. We're just gonna say script, and we already have function, but we'll move it down to here. We don't need that. Base visitor. And we're also going to store a reference to the compiler itself, so. There we go. Then we're going to initialize the reference. It might have been cleaner to just have a pointer to the compiler, but I'm committed at this point. Okay. And we're going to move these functions over to here instead of just as node member functions. Because we might actually need to create new values, and to create new values we need the compiler context, the greater compiler context. And we also want to move these ones over as well. So all of these that are now errored out because they're no longer member values, we're just gonna put under here. And tell them, hey, you're part of the compiler context now instead of compiler. And this needs to be AOT value as well. TOT attack on Titan attack. And it's no longer a member of compiler. So we can just do that. Alright, let's just start at the top and work our way down now. This is an AOT value. With so for compiler, we're gonna make this public. And also gonna make a getter for types. So or actually what type? We'll just copy the type. Hey, it worked. And there we go. So now we can just access compiler types. So, value index plus plus. Cast temp T value. Add some assertions in there, just so that we know we are currently within a function. And this is register local value for one that's within a scope. And scopes is not a private member, so we're just gonna remove that / there at the beginning. What is the problem? Ah. And then we will be done. Yeah. So now, when we generate our bytecode, instead of just passing in the script, we're going to pass in a context, and we can do reference. Like that. And we no longer need cast temp as a member function because that's now part of the context. You can just delete that. Context reference. There we go. So we're just gonna move this to here now. See, so rename this to context. So ctx.castTemp. Oh, haven't included it yet. Let's do that. Here we go. So context cast temp, and then function append code. And then, since this is a node specifically for addition, I'm just gonna function add. And that is exactly what we had before in the compiler, but now we can just store the actual operation tree in actual tree. So let's do this again for addition, subtraction, and multiplication and addition. Division. Anyway. Why is this throwing an error? Oh, I'm just gonna guess it's a problem with the compiler for now. Or the IDE. Well. Oh, it's... yeah. Now, actually, default constructors, perfect. Now, we just generate bytecode, and it's this exact same thing, but with a different operand. Add sub mul div. Not div. Div. There we go. And what we are going to do next is just create nodes for our value. So we're just going to say AOT value nodes. Delete our default class and just gonna include AOT node. And then let's actually create an assignment operator here as well. That way we actually have like, ooh, we added new features. So I'm going to include memory here as well, because we will use that later. So I'm just going to copy... Actually, I'm thinking about it. I could just use dual arg node. I'm gonna move these just to AOT node because I can use them in more places than just in well, no, I could use them in We're gonna put the assignment operation in here. This we're just gonna keep for constants. So class, we're going to just copy the definition because it makes it easier. This const. Now, do I want to have a different node type for every constant type, or a singular constant node? I'm gonna go with one node for now. AOT const AOT node. I'm not a fan of standard any, but we're gonna use it just because it fits this too well. That's gonna be our value. AOT const. And we're going to initialize this with a value. All right. And we also need to have a definition for optimize as well, even if it does absolutely nothing. And if I have enough time by the end of the stream, we can look into doing some like default or some simple const, I don't know what the term for it is, constant expression pre-calculation stuff. So, actually we don't need to, just value, standard, move, value. And on optimization, okay, we did mark that as override. Optimize, we're going to return, just return this, no optimization. Because how do you optimize a constant? It is literally the most optimal thing in this entire, code or whatever. So, now how, okay, include. Now how am I handling constants? Or how am I going to? That is the question. Because there are, so let me actually bring up stuff so I can explain my thought processes. The library I'm using for generating actual bytecode is called ASMJIT or ASMJIT. And let's take in addition or add op, for example. Let's go to the compiler. So let's take this add operation, for example. Right now, the way I'm doing constants is that time. So on an add operation, we just get 2 general purpose registers and we just add them together. So the way we do constants is I have this move constant operation, which pulls the constant out of memory. So right now I'm just storing it in a vector. I'm going to actually store it in the bytecode later. And then it stores it in a general purpose register. Now, this is it's a bit of like a kind of, it's iffy because we can optimize it even further. So Asimjit, it actually has this add function has overrides where, well, actually the override is right here. So this move operation, if it pops up, you can see we have a general purpose register for the destination and a actual memory value as what we're moving into the register. Now, right now, the addition, because of just how I built it, can only handle adding together registers. However, I want to be able to also be able to handle memory. So this is where the whole thing where instead of storing just unsigned 32-bit integers in here, I would store value indexes, where you can store the value type, and then actually I'm just gonna call this index, and then we can add another unsigned integer here and just call this flags. And then we're gonna be able to store whether a value is a memory address or a register with this, or the type of register. We're just gonna say type of register for now. So value index flags uint 8. So we already store the value type. Okay, so we don't need to store the value type in the flags. So for now, we're just gonna have we're gonna have a singular flag, and we're using flags, so maybe we can add more stuff in later. But a value index flat value index flags mem equals 1, and value index flags register is 2. Well, no, not 2. Well, technically it'd be 3, but we're gonna be fancy and bit shift it. So there we go. We now have our value index flags. So we're actually gonna have this be value index flag. Like that. And hopefully the size of this thing will only be the size of an unsigned 64-bit int. Because we got 16... Actually, no, it'd be 32. Yeah. So same size as what we were using before, but we're not going to need more than a 16-bit int to store indexes unless people are using a lot of values in their program. And I don't optimize it well. So unless you have... Let me look this up real fast. uint 16 max value. So unless you have around 65,000 local variables and temporary variables that you've managed to shove into a single function in your script, unsigned int 16 is going to be fine. So, going back, where was I before I went on this whole thing? Ah, yes. Wait. Where was I going with this? Huh? Oh. I am streaming coding at the moment, so yeah. You've been distracted by the roommate. Alright, where was I? Right. So the AOT value is basically the result of the register. So how do I want to... So when we generate bytecode, this AOT value I think I have it. I think I just realized what I want to do, and that is in compiler. No, wait. No, AOT node. When we define AOT value, instead of value index being an index, this is where we actually store this is where we store the value. So, un momento. Thinking. Right. Value index. I shouldn't have needed to think that long for that, but so we now have the value index, and we store this in the ahead of time value. We'll just give it a default constructor. Now, when we generate bytecode, so we're going to have a where do I put this? It is in the script function. So instead of having a move constant enumerator, we're going to have a load C operation, load constant operation. And all this does is it isn't actually any bytecode. This is what will register the constant with the assembler. That's what I named that class, or the runtime, or whatever. It just gives us it loads the register. So going back to compiler, we are also going to need to store so let's just quickly rename this to register index, even though we can just treat them as regular values since the library takes care of actually storing them in between it takes care of everything, so we don't actually need to think of them as registers, but we're gonna, yeah. So we have our reg indexes and mem indexes, and now going all the way back to our value nodes, we can create a, let's add this to compiler. AOT value new constant. These are compile flags. This can store runtime flags. Actually, we... Const expression. So runtime flags would go in value index. Okay, so we're going to rename this to new reg, or new register. And then this index is going to be new register index. Value index dot value type. So we'll also need to pass the value type. Well, actually, type is there. So where do I use this definition? Okay. So def dot value dot def. I have too many different, I need to consolidate enumerators. So value type. So we're gonna just get rid of this. Here we go. Got rid of that. Let's see, what is this unimplemented pure virtual type? But it is implemented. Ah. There we go. So now let's keep pressing back until we, okay. So we have fixed type def to actually be useful. We're just gonna say if not valued is void, because we can return void values from operations, so we just need to safeguard that we're not taking up value or registers. Value flags or operation value index flags. This is a register. Alright, so now we're just going to create a new function that is exactly the same thing, but for constants. New const. Now, there will... Constants don't need... They do need indexes, though. Ooh. No, wait, this comes after optimization. I don't need to worry about that. Alright. We're going to put this right underneath new register, because it is the exact same code, except for... we set... this. Well, why did I just copied from the function above the function that I just... I'm gonna set this flag to mem instead. Mem index. Actually, wait. Okay, we don't just return right there. Never mind. I was like, oh, if it's void, we just return. Actually, we wouldn't be able to return a type that's void, so we can just... if type is equal to void, we just want to return out of here. Or even throw an error. For now, I'm going to throw an error just so that I get annoyed later and come up with a better error handling system. Runtime error. Cannot create constant of type void. Now, going all the way back to the operation value nodes and the generate byte code here. Oh, that took too long. CTX. New constant. Of value type, and then if value dot type is equal to We're just gonna have to do this manually. Just giant else if block. So type ID of int 32t, then type is equal to value type int 32. Then we can create a new const of type. And then we're gonna, well, actually, we don't need to pass in flags because, I mean, it's a constant. It's in the name of the function, so unless, well, there would be other flags we want to pass in, but we can just automatically set the flags. I think. Oh wait, I want this to be value index flags. That was nearly a huge bug right there. Okay. Change this back to a event 8. So I'm just gonna put them here. And which set of enumerators is it? AAT value constant. Okay. There we go. So that's just how I'm gonna set that there. That way, if you want to override it, we can. Now, back to here. Constant, we don't even need to do this. We can just say value type. Since all the constants were going to be, wait. No. Yeah. So if type is equal to value type, oh, I don't even have it set as a type. Okay. So we don't completely eradicate that runtime error. And that. Actually, we do need to... Wait a second. We do need to set the value definition. So we need a way to be able to grab native types or just do this by string. But I don't want to just do it by a string. native types. I'm just gonna create another thing here, which is just no type def get type def value type. And this will be a pointer. And we'll create this right under here. Just switch on type. Thank you, editor. And so for int32, we'll just return native types 0. And then I can update this whenever we have a new type. All right. So back to here. Actually, no, here. Is this working? No, it's not, because we need to do value def equals get value. No. I just named this function. What did I name it? Native types get type def. And then I'm just gonna assert value def real fast. So now this, well, we can just do type. Okay, that should be working now. So we're gonna go back to const. And let's finish up this if-else statement. Type ID is float. We're gonna say float 32. If this is, what other types do I have here? Actually, let's do int 64. Type is a float. All right, now, honestly, I should just call this double, but we're not going to handle that right now. Const function. Not to do that anymore. So append code, script function, load constant. Then for operand, I just realized I might need to do another switch statement. I don't know if we're just going to move this down to here, this is what we return. And then in here, we're going to say type. Load constant value standard anycast int 32t. And that will actually generate bytecode that will store the constant in the actual code instead of the stupid thing I was doing before, which was in the intermediate script. It wasn't the... Okay, it was in functions that I was storing... There it is, constants. Goodbye. Much better, much cleaner. 10 out of 10. So we're going to go back. And you know what? Why not just flesh this out now? Int 64. 64. And here, float 32, float 64, double. Variable type is uninitialized whenever if condition is false. Well, we're just gonna have to live with that. Then I'll need to do one more for strings, but that comes later. That comes like in 3 days, not now. So we now have the bytecode generated for this, and for the const node, I actually am going to have a way to return the value. And let's actually make this a const reference. So now the nodes beneath this can access this if they detect that it is a constant node, and then do whatever they want with that. And I just realized that I have this whole node type system, but I haven't actually been used. I don't even have the variable set up for it. Node type, because that's how things would detect that it's it. But I mean, they could do dynamic casting, but I don't know. This seems like the more responsible way of doing this. So we're going to void, no, node type const And this will return type. And just to make sure this is actually getting set by everything, we are going to force a constructor. So now, going back to operation nodes, all of these are going to start complaining. So now when we do add node, and now on our constant, we're going to need to do this as well. Just like that. So now we can do a switch statement using the enumerator. That's my justification. So now let me just check a few things, and then we can switch over to the whatchamacallit, the actual assembler that generates the script. So verifying we are serializing value indexes. Very good, very good. These take up the same amount of space as a 32-bit integer. All these, so these add, subtract, divide, and multiply. Now, in their actual operation on the compile side, they actually have the type that they're operating on. Because before I was kind of split between putting the types into the I was split between putting the types into the actual bytecode or just having different operands for every single type, but then I'm like, there's a lot of optimizations I could do if I just put the types into the bytecode after the fact, so this is what we are going to do. Alright, so now all the stuff we need to do, well, we do need to move this over to the compiler. Do I want to do... Yeah, let's do compiler first. So let's break all of this code that's already broken. Look at all those red lines. So up here, we're just gonna forward declare this as a just a unique pointer for ease of use. And then in compile, okay. Script compiler reference. Okay. This needs to be that. And then we will just return context script like that. And then every time we run compile, we can actually reuse the compiler now, since we divorced the state from the actual compiler itself. I don't have an assignment node yet. This will come later. I just want to get to a working stage, so we're just going to comment this out and return empty. Visit addition subtraction. So now what we're going to be returning from these are AOT node pointers. And then if this is a addition, we are going to node is equal to new AOT add node. Just like that. Okay, so we need to import AOT operate, no, AOT node. Operation nodes also include AOT node AOT value nodes. So now in here, what did I name it? I just called it an add node. All right. I think I should prefix these though. in compiler, it should be fixed. And there we go. So now we just return node. And let's actually copy this, and I'm gonna move this so it's actually near the addition and subtraction, because they are essentially just the same node. Multiply. If we visit a constant int, we are going to return a, well, new AOT const with an int. Just make sure this is an int 32. Alright, so we need to create another value node that is for variables. And this node is just going to store a value index. And then this also has a actually we wouldn't ever need to return that. We would just generate bytecode like that. AOT node here, value to the list of our node types. There we go. Right. And I'll just put a to-do here to remind me to, when I'm actually going over optimization, what optimization I want to do here. If stores is if this is constant, we just want to return a constant node. Now let's generate bytecode. So the bytecode for this is actually going to be nothing. We just return the value, or the index. AOT value. Or CTX try get value. Right. Wait. Wait a second. So we have our local values, which are stored by a string. But that node how do I want to do this? I'm going to move scopes. I'm going to move scopes back to the compiler. And then all of these scopes, since they actually have to do with strings and whatnot, I'm actually going to put in here, because the names of variables is something that only exists on the actual compiler side. So all of these, let's see, compiler, context, compiler. Because the abstract operation tree does not need a concept of what a scope is, because any of the operations defined by scopes could just be shown in the actual abstract operation tree and thus be able to be optimized and whatnot. So when we visit an ID, what we're going to do is we're going to get a value. I'm just thinking this through. What would be the most optimizable way to do this? So when we visit an ID, let's actually not worry about the... Let's not worry about the name of the variable whatsoever. And then we're gonna try get value. AOT node equals, and we're gonna rename this to AOT node and the name of this node is going, or the name of this is get value node, and we only need to put in the name. And then in our actual scopes, we are going to, instead of storing the direct index, the value and everything, because that only exists at the, when we're running through the generate bytecode of the nodes, what we're going to do here is just store the nodes. So all of the operations that are referencing, wait, I can't have them all reference the same thing because since nodes are stored in unique pointers by their parent nodes, they would get deleted the first time an optimization takes the... Well, actually, you wouldn't really be able to optimize it out. Actually, you might be able to optimize. I'm going to assume that you're able to optimize out variables. So we're not going to point all of them to the same place, but we are going to... How do I store the... How am I going to store the variable index? We're just gonna do 16 since that's the biggest it can be, and just have that as our reference for just the local variable itself. And since it's independent of scopes, well, it's just an ID, so I guess it's fine, I guess, maybe? Be a lot faster than using strings, so this is what we are going to do. Actually, we could just do... Alright, let me think through this. So, node... We're just gonna call it L value index because that's basically what it is. Because eventually I do want to allow for global variables within scripts. So L value index would take care of that as well. So what we are going to do is local values, L value index. All right. When we visit an ID, going to get value node context text. And this is going to return an AOT node pointer. Pointer. And then just return new value AOT value node. And then in the value nodes, we're just going to store the L value index. uint 16 type L value index. There we go. And now when we generate bytecode, now is when we get the actual value from the context. So compiler context. Do I have to come up with a scope system here too? No, because every single one of them is different. So I'm just going to pull out the standard map uint 16t. It's going to be faster to hash than a string. And this is just going to be a t value. L values. So now back in here, I also need to store the type of this variable. And then I would also want to store some flags about the value as well. Like, is it a constant? Is it a... For now, we'll just store it as a Boolean. And now in the compiler, I'm just gonna straight up store a value node in here. And then when we register local values, we also need to do value type. And if it's constant. What am I holding in my... Okay. Music stopped. Let's start it back up. Which mix do I want to do this time? Let's do... this one. Got some night drive synthwave going now. Value node. L value index plus plus value constant. Now if we go back to the value nodes, now when we count the value index, we can just return values at value index. Otherwise, we need to create a new one. Equals context dot register. And the type is... Alright. Since we will eventually be able to have user-defined types, I should just have string here. String type. Then here, oh, I've lost the reference. There we go. Dang it, was that only one song? It was only one song. There we go. AOT value, add context new reg, and then type. Wait a second, why am I accepting strings from new register? That's right, because we have the value definition, which could have, like, defines, like, operators and whatnot. Okay. Or will define operators. At least that's my plan. And functions and whatnot. Okay. So this is fine. I think. Yeah. This is fine. So context, new register of this type, or a new value of this type. And then we also add in flags, where, okay. For now we just have constant, so constant then value index flat. No, wait. AOT value const. Constant is only on the syntax side. We would only care about it. I'll refactor that later. Not gonna worry about that now. Then we're going to insert this into there. Context L values insert. Value index value. That is exactly what we want, I believe. At least that should work. I hope. Wait a second. Did I never move these? I thought I said I was gonna move them. Oh well. So one last thing we need for our demo is AOT return value node. AOT single arg node. All right. This would just be this would just do context dot function append code script function ret v return value, and then into here we just pass arg generate bytecode context. All right. We actually wouldn't return anything from this function. We'll just say it returns that value. I'm gonna get rid of that Discord ping. All right. Wait, what? Oh. This will show up as null since we're not setting it to be void. Should have everything I need now to go through the compiler and replace everything with nodes. So we already did subtraction, multiplication, constant integers, visit ID. Okay, visit ID is what we were working on. If not, node. Declaration. Is it function? I'm gonna do that one last. Visit return void. Currently this is not doing anything. Just gonna put that there. That will be fun to run into later. Visit return value. We are just going to return a new return value node with a return value. Needs an AOT node as an argument. Oh, AOT node, right. Register local value, AOT value node. fixed. Now we can go back up to, it is only the visit function that is now running. So, context function gets to be a new script function. And then previous function. And the reason we store the previous function and then switch back to the current function is so that we can define stuff like lambdas later on. Pretty sure this had local functions. What was it before? Did I accidentally? Oh, this is the script function itself in here. Alright. So we need to get rid of this register constant since we are storing it directly in the bytecode now. So we want script, intermediate script, that's what we want to look at, local functions. Function is just context function. The reference function and then oh no, scary raw pointer memory management. Context L values. Want a new register, that's what we want. And then So here's where we go. Context. New register. Wait, no, this would be L value, right? Wait, new register does take a string. What am I freaking about? What am I freaking out about? So, insert. Alright, come on, Brane. What are we doing here? Text. Wait a second, this is a compiler thing, so register local value. That's what I want. And here we put the get text. String value, or type, that should be type. And this is not constant. Alright. That's working, I think. Let's just quickly rename this to type. Yep. We now need to gather the entire tree and actually execute the optimization, or not optimize, do the thing, do the thing. So now we need to flesh out this visit expressions. So let's go to compiler, visit expression list. vector of nodes. This list of nodes. Now we just need to quickly check to make sure everything that we care about actually returns a node. So function index. I'm not going to mess with that. So in the future I'll have a toggle where you can have the compiler optimize or not optimize, but for now we're just going to always call optimize. And we're actually going to pull a fancy on this one. Since all of these are just pointers that are not managed, they have no memory management. What we're going to do is name this expression. This gets to be, we then put it under the care of this unique pointer. And then when we optimize, we just let well, no. If expr so if our optimized tree is not equal to the original node, then just grab the we'll just create a new pointer. From optimized tree. Like that. So now all of that is now optimized. We aren't actually doing any optimization yet. But then we can just call tree generate bytecode. We're gonna pass in context. So this right here actually generates the bytecode. And theoretically, it should just work. Let's run it and see where it. Wait, I haven't redone the interpreter for the. No, not the interpreter. The assembler for the new. Yeah, we haven't redone the thing that actually creates the stuff. We haven't done the thing. We haven't done the thing yet. My brain is forgetting how to talk. So what I'm going to do... This is going to be a let's see, where am I holding? So this is where we're holding labels, registers. We're just going to call this constants for now, though in the future it might also include global variables. But for now it's just constants. So now when we load constant, what will happen is instead of actually doing anything, what we're going to do is first value index constant, and let's import this library, or struct. There we go. So value index constant. What am I? Okay. I'm just gonna put this like here. So now when we gonna load this as a value index, because the value index is now written into the bytecode. Actually, let's go down the list thing by thing and just fix every single one. So this one needs a value index instead. the register type doesn't actually matter. Actually, it does if we just need to... If val index dot flags and value index flags register, we want to do this one. Turn get register val index dot index, and I'm actually going to change the definition of this so that index is a 16-bit integer. How do I printf a short? H modifier. Alright, so I just put an H right there. Oh, okay, it's complaining about that. Index. There we go. I'm actually going to include the printf in here just for now and debugging purposes. I'm gonna put an R there just to say it's a register, and then this is just an else, which means we're just directly returning a memory. So here what we do is, instead of all of this, we just return constants at val index dot index. Oh, does it need to be a register? It does need to be a register. Okay, so for return, it does need to be a register. Now, do I want that to be an extra instruction, or do I just want to bake it in? I'm gonna bake it in just to make it easier. Actually, no. We're not gonna bake that in. But we are going to assert this. So then, just to make sure that that never throws an error, let's go back to the compiler, return val, and value node is what we want to deal with here. And then cast temp. We're going to create a new cast register because it doesn't need to be a temporary value. It only needs to be a register value. So now we're essentially going to do the same thing as we do here. Call it reg value instead. And the thing we want to check for is value index flags and value index flags reg. So if this already is a register, just return it. Otherwise, we want to create a new register and then call a move operation into the new one. Yes. So now let's go back to here. So we cast this as a register and then we return value register. There we go. Now going, where was I before this? We'll just keep, there we go. So now this assert should never fire unless we have faulty bytecode. Now, to load a constant, what we are going to do not going to read the next thing yet. Just going to say load C. Then what values do we want to print out about this constant? Probably the index of the constant. So and then I'm actually going to end this printf after a space. And then I'm going to go into a switch statement, constant dot value type. And for now, we're going to delete all of them but int32. And as default, we're just going to assert, because this is not implemented. And then also going to assert that constants does not contain this constant's index yet. In fact, I should do that. Nope. Right here before doing anything else. We're gonna say constants, constant index equals, create new 32-bit integer constant, and then read out the integer just like that. And we now have a constant loaded into the assembler, or the compiler, I guess. Now, onto the move function. This is going to be very fun. So, same sort of deal. So, auto destination is reading a value index. Oh, I forgot to finish this printf. Alright, now we can move on to move. Alright. And then I'm also going to back in compiler in, let's see, cast temp. We also need to cast this as a register. Wait a second. It wouldn't have the value temp if it was a memory, so we don't need to worry about that. Cast temp will take care of memory for us. Alright, so move instruction. Assert that dest flags and value index flags. This is a register. We need to make sure this is a register, or else this will not work. Well, actually, it doesn't need to be a register. But for now, it's only going to be a register. In the future, for globals, it won't be a register. It will be actually, it will be a pointer instead. Anyway. This works for now. So we're going to switch. And I'm going to start the printf statement here, because I feel like it. Move into R, or register, dest index. And then we are switching on stat. Actually, it's just an if statement. No, it would be on type. We have to... Let's do it on type first. Because this is going to be a big switch statement, so we want this to be at the base level. So for int32 and int64, we want it to be treated the same way. I think we would want pointer to be treated the same way as well. Because those would all be general purpose registers for the base. And then float32 and float64 would both be the same type of register. So let's create some scopes in here so we can define variables. So I'll call this dest source register. And this one is general purpose. The index is dest index. And then eventually this will have to deal with floats and stuff, but source, well actually let's put this at the top. Source is equal to func.read. Actually, I don't need to do this within a scope, I can just do it out there. Read code, value, index. Now, if source reg, well actually we would need to oh, there's going to be so many nested switch statements, and I'm going to have to figure out a better way to handle that. I'm just trying to think through a way to reduce the complexity of this, because I don't want to have this huge like branching structure. But we're working on a proof of concept here, so source dot value type, because for now we don't need to worry about any of the float cases. In the future we will, though. So in this one, we would get the source is just index, like that. With source value type. Wait. String to type. Where am I using this? For the function arguments, okay. That makes sense. Value type, switch on type. Come on, let me do the thing. You're giving me the error, but not the solution. Alright, we'll just copy it from over here then. What type would a pointer be? I'm gonna say int pointer. go. Now in here, we can just put type to assembly type. Just like that. Then we can actually execute the move operation. So compiler, move into the destination reg the source register. And then for the source register, this one will get constants at. That way it will throw an error if it hasn't been defined yet, which it should have been. At source index. Check error, cc move destination register. Oh, there we go, it works. Okay, so that will move the constant directly into the variable. This is like the sort of optimizations I was talking about, where instead of taking 2 commands, instead this only takes 1. So instead of having to load the constant into a register, instead it's just load the constant into a register and then load constant into register and then move that register. If the register is moving anywhere, you can just straight up move the constant. Though this will become more prominent for addition operations. I really do need to figure out a way to reduce all of this. Because I do not like this. So we can now delete this. And now we finish up the printf. With either a register, or we finish this up with a memory index. Just like that. Alright, I'm figuring out a better way to do this because I don't want to have to go through that entire operation for every single one of these. think I'm going to create a compile definition for this. Type. And then I'm going to say general purpose. General purpose. There'd actually be a ton of things there. I'm actually going to define an enumerator here. This is going to be operand types. And general purpose operations. We have general purpose mem operations, mem general purpose operations, XMM or general purpose XMM operations, XMM general purpose, XMM memory, then memory, XMM, and there's no such thing as a memory operation. All right, and then we'll just create a function that gives us one of these, given two different values. So we'll kind of say operand type, and into this get operation type, value, index reference A, value, index B. And let's make these constant as well. So we're gonna switch on A dot value type. Actually, let's just do if A value flags and value flags mem. And we're also going to copy this. Yeah. So now, if A is mem, we're just going to go straight to a switch of B dot value type You know what? Thinking, what if I do something similar to constants, where you essentially define the type and thus the register ahead of time? Oh, well, I can just optimize this later. It's fine. It's fine. So if any of those, return mem gp. If those, mem xmm. All right, and then for this one, I'm just gonna copy this because it's pretty convenient. And then we can actually just copy this same switch statement again. Actually, I can make this even simpler. General purpose XMM mem. And then just value register type get value reg type value index reference value. And then we pull this switch statement out right here. If value if we have value flags mem, just return memory. If otherwise we switch on value type, return it. We're gonna make this one a enum class. Here we go. And now when we do this switch statement down here, it's going to be a lot simpler. So we can just get rid of that. Switch on zero, 1, 2, and we're going to base this off unsigned byte. So we're going to switch on get value register type of A. Then value reg type mem. I'm actually going to pull something here. We're going to create a pointer here. Just to decrease complexity. Type map is equal to GP XMM GP mem. if I pull this? Nope. Pointer. I was gonna say. No, it doesn't need to be new. How do I have this point to a constant string? Okay, we'll predefine all of them. General purpose, XMM, and mem. Just like that. And then we're gonna create a const operation type pointer type map. Type map equals GP map. Oh, music stopped. Let's go on to the next one. There we go. Now we just have a second switch statement below here for B. And if the register type is GP, return actually we could just return type map 8. Just like that. No switch statement. It just works. I was about to be very confused if I hadn't caught that. Now, if we go down to here, instead of this... Oh, no, not here. If we go here, instead of doing this weird switch statement here, we can just do one. So we can switch on get on operation type between dest and source. That is the most vague error I could come up with. Not on purpose. So for case of general purpose, general purpose. The source is general purpose, and the destination is also general purpose. There we go. Now we can just copy and paste this for memory, since that's the only one that we're going to need to worry about for now. And we can add in more operands later, and it's all just going to be in one flat switch statement. Hallelujah. So the source register for this one is going to be from memory. So just constants dot at source.index. And then we can delete this. Look at that. It's beautiful. Much better than it was before. And then I can actually copy this. And I'm actually going to change that to be memory. Now for add or adding. It's the exact same code. A, B, A dot index. This is B. This is B. A, B, A. And then instead of move, it's add. And see, this is where the real speed comes in, because this optimizes even this very small one, because instead of constant to register and then that into the add operation, now it's just you add. Do I still have it up on the terminal? No. Output messages. No. Debug, yes. So you can see here how we have this move constant multiply, then move constant, and then add. Instead, we're going to have a load constant, which does not translate into any machine code whatsoever. It would just be add, subtract, without the actual machine code for moving that. So pretty significant speed up, I guess, for a thing this small. And now I can literally just copy this code and change the function name for the other operations. Sub. Multiply. Here we go. So theoretically, it should now work. Alright, it built. Visit ID. Could not find identifier. So what I should be checking is this. that is not what I want. So argument. So there's argument type, and then there's argument name? No. ID. Yes. Yep. So that is now A. This time it found the node, so that was that error. So bad anycast. So on the right of this multiplication division, let's figure out so we get an AOT const. And that should be fine. No, it's not. What was the left then? Dang it, I skipped it. So on the left side of this operand was an inline. Oh, okay, so that would just pass it right through. Visit that, and then we visit an addition subtraction, which worked just fine. So, wait a second, let me check my source code, or test code. I think I know what the problem is. I think I know what the problem is. So we have A minus B here, and in the compiler, whenever we visit a value, we return an AOT node pointer. However, in this one, in this one, we return a constant, or an AOT const pointer. So the standard any node is recording that as a pointer to an AOT const, not a pointer to an AOT pointer, because it's not able to automatically downcast apparently. So we're just gonna have to pull an AOT node pointer here and just cast every time we return a new. Wait, return val. There we go. let's test if that fixes it. Yep, it did. That was the problem. So it ran and it compiled. Let's check if that is the correct result. Just make sure that we're actually getting everything. Also, my formatting is bad. So load int. So it's constants that are breaking this. Load const. Add in a new line here. There we go. Let's run this again so I can see the bytecode clearer. There we go. Why are there so many return values? Did I forget to break? Load constant. No, I still break. Why are these all showing up as returns then? Okay, that makes no sense. So the first thing we do now is we move register 2 into register 2. Then we subtract actually, let me rewrite all the print statements here because some of them do not make sense. So print move, and then print HU, because this is dest, and then okay. And then for this one, we just replace M with that. Memory. Okay, print statement should be fixed. Alright, move register 0 into register 2. Subtract register 1 from register 2. Then we load. Then we load 6. An integer with the value of 520. I'm just gonna make sure that I'm using the correct format code for that. So for constant, let's just do I for fun, and then value is 32-bit int. I'm just gonna put that there, even though it's gonna complain about me, complain about my formatting. What was I going to look at, right? I was going to get rid of the Discord ping again, or figure out what it is. Alright. I'm just gonna pause right there just to see, is the integer, is value actually, yep, it actually is 520. That's not good. So value nodes. Oh, okay, I understand what's going on. I don't know how that worked at all, but that not throw an error. Well, I mean, it was returning every single thing, so that would do it. Value. Switch on value. Switch on type and just copy these over. And the thing is, we want to serialize value, just like that. variable, it's something else. Value index. Oh, right. There we go, it's actually working now. An error hath occurred. Right. I remember. Let's see, where was the script function? Script runtime. So I know what the problem is, I'm just researching why, because when I figured out how to fix it, it was while on an airplane without access to the internet. So to fix this, the problem is, for some reason it doesn't like the default multiplication instruction, so you multiply immediate, or divide immediate. I'm just trying to figure out what is the actual assembly language reason for this. I'll figure this out more off stream. But for now, wait. It was idiv, not multiply by. So maybe it wasn't directly. Okay, and more googling. Single operand form of signed multiply. Wait a second. Oh. Okay. That makes sense. It also makes sense why I didn't run into that while... Okay. So the regular multiply assembly language instruction, this just mul, is for unsigned. So unsigned is the default. And then int mul or imul or however, it's the signed version of that. That makes more sense. Okay, so... Wait a second. I might be big dumb. Let me check if I'm big dumb. I am not big dumb, I think. That would have been an easy fix. Let's see here. R2, R1. These are never doing the versions with memory operands. So let me do some digging here. So the first one is subtract. So the subtract should work just fine. And then multiply. So let's break at multiply. And let's check out B and A. Both of these are registers. Alright, so for some reason, the value index being input into this multiply does not have the mem flag set. Look at the value nodes. For constant. So at const value index, and then we return this. And we apply the memory value flag. So the memory flag and the register flag were the same flag. That is now fixed. It should no longer be like that. So this, the value index flag 1. So that is the correct flag. And then if we continue, after that's cast temporary, both of these value indexes flags should be okay. They are both now 2. So yeah, flags are now actually working. However, still showing up as registers being multiplied instead of the memory index. So let's check that out. So the flags are different on the 2 variables. And then let's see about this. So the first register is a general purpose register. So we go there. Which means the type map gets set to that 0, 1, 2 slash Alright, let's do some digging. So get value type B should return mem, but it returns general pointer. Okay. Interesting. So that's our error. Or general purpose register. So value type mem. Wait. So that is B. Okay, so that is the correct flag. Wait, what? I need to be checking the flags, not the there we go. It's working now. Or it should work now. Let's run this again. Get operation type. Get value reg type. B. It now returns the correct value. And now if we type map that, it returns the correct value. I wonder if I could even get away with not casting this. I can't. All right. So now we are in business. There we go, it's working. And theoretically much faster, because this isn't an actual assembly code command anymore. It's just constant. that is the correct thing. So you can see we're first remove register 0 into register 2. This is because register 0 is a variable and we want to preserve its value. We then subtract R1 from R2. We then load 6 as a constant. We then multiply register 2 and constant 0. We then load 2 into constant 1, and all of the constants would have already been loaded in before this, so no actual operations. And then yeah, so the bytecode is correct, the operation is also correct. We could even try out messing around with our order of operations here, messing with the syntax and whatnot, running it again, no issues. Let's go. Now the question is, am I done or do I keep going? So I'm gonna try something first. So we're gonna move this over to the left side of this operation. And the reason I'm doing this is because the way the node tree works, I'm gonna break out the paint. Or actually, I don't even need to break out paint. I could just bring it into the preview window. So this is what the abstract syntax tree. Can I zoom in on it? I cannot zoom in on it. Yeah. So anyway, you'll have to kind of squint, but the way the nodes work, just this will be a lot easier to simplify. If I had it on the other side, what I'm about to try is it wouldn't immediately what's the word I'm looking for? It wouldn't work immediately. So we're gonna try optimizing this out of the program. So we're going to be looking at the addition and multiply nodes. So we're just going to do subtraction node first. And we're going to override the optimization. Actually, AOT node enter. I think that's it. Yeah. So we're going to run the base optimization first, because that takes care of like children and whatnot. And as default, we're going to return this. So if arg A type is equal to const, and argb is also equal to const. This means that both sides of this expression are constant, and it's a deterministic equation, so we can just return, well, we have to check first if it's numeric. So we're going to dynamic cast from the thing to a const B as well. If a dot value is equal to dot type is equal to because we want to make sure that we preserve type. So if a dot value dot type is equal to b dot value dot type, I'll just do that first for now. If a dot value dot type actually, let's just pull the value out here. A dot type equals type ID of int 32t, then we can return a new AOT const node with a value of any cast not unsigned 32t a minus b, essentially. And we're going to do the same thing with float as well. Why don't we do a double while we're at it as well? And I'll worry about casting and whatnot later. But for now, let's just see if this works. It worked. First try, too. So we can see that immediately, instead of subtracting 4 from 2, we immediately just load 2. As a constant. Sensational. And let me show you what I was talking about before. So if we put this optimization on the other side, it won't work because this addition will try to happen first. Well, this addition, because it's that entire block of code, because this executes first, and then this, and then this. So it has the impression that what am I looking for? This entire thing has the impression that this is not constant, where the entire expression is not. But if we were able to peer deeper into the node structure, this would show up as a constant as well. So I need a way to be able to optimize that sort of thing in the future as well. But I think that's where I'm going to leave this stream, because we actually got a lot done and got it working all within the stream. So added AST. Okay, we're actually going to move this to the other side, so it's actually showing off the optimizations we did. Added AOT optimization. And implemented value indexes. There we go. Detached head. Why is it trying to... I didn't make any changes to this, did I? I'm just going to add this to the git ignore. Actually, no, I shouldn't need to because it is a git submodule. Anyway. Shall commit and push. Well, shall just push. And there we go. And I'm also going to check out the update remote. Oh well, that's where I'm gonna end this stream. Got a lot done. Good stream. I will see you guys next time. I'm gonna try to keep streaming somewhat regularly throughout the week, so hopefully this will become a more frequent occurrence.